Let's talk about how we can show that two triangles are similar to each other. It might be easier than you think. You might remember in our last lesson that we learned that in order for two polygons to be similar, we should show that all of their corresponding angles are congruent and that all of their corresponding sides are proportional. But the good news is, in order to prove that two triangles are similar, you don't have to prove all of that information. We're going to learn three theorems that make things a little bit easier. The first is the Angle-Angle Triangle Similarity Theorem, or AA squiggle. If two angles of one triangle are congruent to two angles of another triangle, then those two triangles must be similar. We actually don't need to show that all three angles are congruent, because we could figure out that the third angles were congruent to each other using the triangle sum theorem. Remember from first semester that the sum of the interior angles of every triangle is always equal to 180 degrees. So if, for example, we knew that this angle was 60 and this angle was 70, well, this angle would have to be 50 because of the triangle sum theorem. So if all I know is that I have these two angles are congruent to these two angles, well, if this one is 60 and this one is 70, then that one has to be 50 as well. I didn't have to show that these two angles were congruent to each other, because I could end up proving it using the triangle sum theorem. So this is a super quick and easy way of showing that two triangles are similar. If you can just show that they have two pairs of angles that are congruent, then the triangles must be similar. But that's not the only way to show that triangles are similar. You could also use the Side-Side-Side Triangle Similarity Theorem, or SSS squiggle. This theorem says that if all three pairs of corresponding sides are proportional to each other, then the two triangles must be similar. And the cool thing about this one is it works for all polygons, not just triangles. So you could say if all four sides of one quadrilateral are proportional to all four sides of another quadrilateral, then the quadrilaterals are similar. Or hexagons or dodecagons or whatever you're trying to prove, this one doesn't just work for triangles, it works for all polygons. And our last theorem is the Side-Angle-Side Triangle Similarity Theorem, or SAS squiggle. This theorem states that if you have two pairs of proportional sides and their included angles are congruent, then the triangles must be similar. For example, if AB over XY is equal to AC over XZ, and angle A is congruent to angle X, then triangle ABC is similar to triangle XYZ. The placement of this angle is super important. Notice that angle A is in between sides AB and AC. That means it's included, which is what the theorem states we need. If we had known instead that angle C was congruent to angle Z, that's not enough information. So let's take a look at a few examples and determine whether or not the two triangles are similar. The first thing you're going to want to do is decide which of the theorems would be the best one to use based on the information provided in the diagram. For example, here we have three sides labeled, and we know nothing about the angles. So for this one, it seems most logical to use side-side-side similarity. I can't use angle-angle similarity or side-angle-side similarity because I don't know anything about the angles. So if I'm going to use side-side-side similarity, I need to show that all three pairs of corresponding sides are proportional. So let's set up a statement of proportionality and reduce. I'm going to do long side over long side, so 18 over 12, equals medium side over medium side, equals short side over short side. And all of the yellow triangle lengths are on top, and all of the green triangle lengths are on bottom. So let's reduce and see what we get. 18 twelfths reduces to 3 halves, 15 tenths reduces to 3 halves, and 12 eighths also reduces to 3 halves. So since all three pairs of sides have the same scale factor, we can say that the two triangles are similar to each other by side-side-side similarity. Remember that the order of the letters in your similarity statement matters. If I choose to go STU for my first triangle's name, I must go in a corresponding order for the second triangle's name. S to T, that is the shortest side, and T to U, that's the longest side. So if I go short side, long side, I need to do the same thing for the other triangle. Short side is 8, long side is 12, so I would go VWX. Always make sure that you write the letters in your similarity statement in a corresponding order. what do you think about our next example? I have two sides and an angle. Looks like I should be using side-angle-side similarity based on the information that I've been given. But the side-angle-side similarity theorem says that it has to be two pairs of corresponding sides are proportional and the included angles are congruent. The angle that I've been given is not included in between the two sides that I've been given. So these I cannot prove are similar because ASS similarity is not a valid theorem. It's important to note the way that I wrote my answer. I said that they can't be proven similar. I didn't say that they're not similar, because I don't have that information. Maybe they are similar, maybe they're not. I just don't have enough information to say one way or the other. On our next example, we have some right angles labeled. Remember that all right angles are congruent by the right angles congruence theorem, so I at least have one pair of congruent angles. And the other information I know is also angle measures, so it's looking like I should be using angle-angle similarity. But angle-angle similarity says that I have to have two pairs of corresponding angles that are congruent. And right now I only have one. Angle I is congruent to angle L by the right angles congruence theorem, but 71 and 19 are obviously not the same measurement. So you might be tempted to just say, well, they're not similar. But hold on a second. Can't we figure out the measure of angle K or the measure of angle M? According to the corollary to the triangle sum theorem, we know that the acute angles of a right triangle add up to 90 degrees. So what do I add to 71 to get to a total of 90? Well, that would be 19. So that means that angle K is 19 and angle N is 19. These are two congruent angles as well. So that's enough information to say that these two triangles are similar by the angle-angle similarity theorem. Again, make sure that you're writing your similarity statement in the right order. If I call the first triangle IJK, well, that went from right angle to 71 degree angle to 19 degree angle. That's the order of the vertices that I picked for the first triangle's name. You can pick whatever you want to for your first triangle's name, but whatever you pick, your second triangle's name has to go in the same order. So if I go 90 to 71 to 19, then I again need to go 90 to 71 to 19. So that would have to be triangle LMN. On our next example, we're given two pairs of sides and their included angle, so it looks like a side-angle-side similarity situation to me. There's really no work to do to prove that the angles are congruent. They're already marked, so that part's good to go, but I need to show that my corresponding sides are proportional. So I'm going to set up a couple of ratios. I'm going to do short side over short side, so 24 over 16 is equal to long side over long side, 33 over 22. And if I reduce those, I get 3 halves. Since their sides are proportional to each other, and remember since our included angles were congruent to each other, I can conclude that these two triangles are similar by side-angle-side similarity. Our next pair of triangles, we know all three of their sides, but none of their angles, so that looks like a side-side-side situation to me. So the first thing I need to do is set up a statement of proportionality comparing all of their pairs of corresponding sides. So I'm going to do long side over long side equals medium side over medium side equals short side over short side. And then I'll reduce. I get 3 halves when I reduce 84 over 56, but when I reduce 80 over 54, I don't get 3 halves, I get 40 over 27. Technically, you could stop right there if you wanted to. That's enough information to say that these two triangles are not similar, but you could also reduce that last one and show that it's 3 halves. Not that it matters, 2 sides isn't enough. You have to show that all 3 pairs of sides reduce to the same ratio in order for the sides to be proportional. So since I have shown that all 3 pairs of sides are not proportional, I can say that these triangles are not similar, which is slightly different than one that we saw earlier where we said we couldn't prove whether they were or were not similar. Here we have enough information to say these sides are not proportional, therefore these triangles are not similar. Our next pair of triangles, all we know is some angle measures. I don't know anything about the side lengths, so that leads me to angle-angle similarity for the best theorem to use for this job. But I only see one pair of corresponding angles that are congruent. 28 and 28 are equal, so H and T are congruent. 60 and 93 don't equal each other, so you might be tempted to say that the triangles are not similar. But remember, you can always calculate the third angle in any triangle if you know two of the angles first. So I could say that the measure of angle G plus 60 plus 28 is equal to 180. When I solve that, though, I get an answer of 92. You could have also solved for angle R instead. The measure of angle R plus 93 plus 28 equals 180, and I find out that the measure of angle R is 59. But that's not 60. So in this case, I have shown that since I don't have two pairs of corresponding angles that are congruent, I only have one pair of corresponding angles that are congruent. That is enough information to say that these two triangles are not similar. Let's look at a couple examples that are a little bit different than the first few that we've seen. So far we've looked at triangles that were really not connected in any way to each other. They were just two random triangles on the page. Now let's look at some triangles that are basically built on top of each other. And there's a couple different ways that I could go about proving whether or not these are similar. I see some side lengths, but I don't see all three side lengths. I don't know anything about DE or BC's lengths. All I know is that they're parallel. So it doesn't look like I could use side-side-side similarity to prove this. But I could use side-angle-side similarity. First, let's compare their corresponding sides and see if I have at least two pairs of corresponding sides that are proportional. So I'm going to put 52 over 28 plus 52. Don't just put it over 28, because if I'm talking about triangle ADE and triangle ABC, 28 isn't one of my side lengths. It's just part of side length AB. To get the entire side length, you need to add 28 and 52. And similarly on the other side, I'll put 65 on top, and then I'll put 65 plus 35 underneath of it, because I need both parts to figure out the length of AC. So when I reduce, they actually both reduce to the same thing, 13 over 20. So since I have two pairs of corresponding sides that are proportional, and I have an included angle that is congruent, remember the reflexive property? Angle A is the included angle for both of these triangles, and angle A has to be congruent to angle A by the reflexive property. So I could say that triangle ADE is similar to triangle ABC by side-angle-side similarity. But that's not the only way that you could have proved this. You actually don't need to do anything with the side lengths at all because of the fact we're told that these are two parallel lines. Remember that parallel lines cut by transversals make all kinds of special pairs of angles. For example, we could say that angle ADE, this angle right here, is congruent to angle ABC, this angle right here. These two angles are corresponding angles. And I could say the same thing over here about angle AED and ACB. They're also corresponding angles and therefore have to be congruent. Or instead of using corresponding twice, you could have used corresponding once and the reflexive property once. Either way, there's enough information to use the Angle-Angle Similarity Theorem to say that since I have at least two pairs, actually three pairs, of corresponding angles that are congruent, these two triangles must be similar. Our next diagram features parallel lines as well. So if these are my two parallel lines, I could treat XZ like a transversal or VY like a transversal. So if I'm looking at XZ as a transversal of these two parallel lines, well, angle X and angle Z would be alternate interior angles. And we know that alternate interior angles are congruent if they're created by two parallel lines cut by a transversal. Similarly, angle V and angle Y are also alternate interior angles, which means they must be congruent. So that is our two pairs of corresponding angles that are congruent, which means I can say that these two triangles are similar to each other. Alternatively, you might have noticed vertical angles. So instead of using alternate interior twice, you could have used the vertical angles congruence theorem combined with the alternate interior angles theorem to make the same conclusion that these two triangles are similar. And that's the basics of what you need to know about showing that two triangles are similar. In the next part of this lesson, we'll explore how to show that two triangles are similar if they're graphed in the coordinate plane.